In this video, we're going to look at gas stoichiometry, or the stoichiometry of reactions that involve gas. This isn't really a new concept. It's just adding all of the things we've learned about gas and calculating number of moles, volume, and pressure into stoichiometry problems. If we think about the reaction of propane with oxygen to give us carbon dioxide and water, we can see that all of those involve gas. We take 1 mole of propane, react it with 5 moles of oxygen gas to give us 3 moles of carbon dioxide gas and 4 moles of water gas as steam. Now we can do this calculation, but since these are gases, not only can we determine moles from reactants to products and also the masses, we can use ideal gas law, PV equals nRT, use the number of moles, and calculate volume, pressure, and sometimes even temperature. We can also consider the fact that this is a partial pressure problem because at any one point we have all of these different gases in our container if we had a closed container. We can see that we could also use Dalton's law, total pressure equals the sum of the partial pressures. Let's look at a problem. Complete decomposition of a pure sample of potassium chlorate produced 2.16 grams of potassium chloride and oxygen gas. What is the volume of oxygen produced at STP? Well, when we look at our problem, we see that it's giving us the reaction. It's going to be the decomposition of potassium chloride going to potassium chloride and oxygen. So we can draw our reaction. Potassium chlorate decomposes to give us potassium chloride plus oxygen. Now, since it's stoichiometry, it's important that we balance this equation. Notice that the equation is not balanced. So we're going to add components to balance it. Here, I'm just going to go ahead and put them in because what we're going to focus on is our formula. So it actually takes 2 moles of potassium chlorate to produce 2 moles of potassium chloride and 3 moles of oxygen. Now, in our question, it gave us 2.16 grams. Now, to go from grams to moles of oxygen, first we're going to have to go to moles of potassium chloride, then we're going to have to go to moles of oxygen. And then if we had to go back, we go grams. So let's look at that first step. So 2.16 grams potassium chloride, we're going to turn that into moles of potassium chloride. Means we're going to have to divide by the molecular weight, 74.55 grams of potassium chloride per mole of potassium chloride. Cancel out the grams, do our calculation, and we'll see that we are going to come out with 0.0290 moles. Then we will take our moles of potassium chloride and turn them into moles of oxygen. So 0.0290 moles of potassium chloride, and we're going to turn that into moles of oxygen. For this one, we're going to need to use our stoichiometric coefficients. Looking at the balanced equation, we see we have 2 moles of potassium chloride and 3 moles of oxygen. We cancel out our moles, and we'll come out with 0.0435 moles of oxygen. So now we have moles of oxygen. But remember that the question is not asking for moles of oxygen, but the volume. It's important that you always read the question and make sure that you're answering the right problem. The problem here is that we have to get to the volume. We know how to get to the volume. If we use the ideal gas law, PV equals nRT, we rearrange to get volume by itself. V equals nRT over P. We have the number of moles, we just calculated that. We have R, that's our gas constant, whereas T, temperature, and P, pressure. In our question, it told us at STP. Remember that STP is standard temperature and pressure. So T is equal to 0 degrees Celsius or 273.15 Kelvin, and P equals 1 atmosphere. Now we can see that. Plug into the formula and we'll be able to calculate our term. So once we plug everything in, you'll see that we have 0.0435 moles times the constant for R times 273.15 Kelvin, that's the standard temperature, divided by 1 atmosphere, the standard pressure. Do this calculation, and we see that our volume is going to be 0.975 liters. Double check all of your units, moles, atmospheres, and Kelvin, giving us liters. Students often have problems with gas stoichiometry. You just need to take it slow. Take the problems step by step. Make a plan for solving the problem. There are a few steps to this. First, make sure you know what the question is asking for. Then, determine what is given and what can be determined from the data in the question. Make a plan before you start doing the calculations. Implement your plan and check for errors at each step. Reflect on the answer. Does it make sense? With the problem that we did, we had 0.043 moles of oxygen, and it came out to 0.975 liters. Does that make sense? Do we have anything to compare it to? Well, we know that 1 mole of gas at STP is 22.4 liters. So therefore, 0.043 moles, being about 1 liter, makes sense. Many of the calculations will make sense if you just think about what the answer is, and is it even the right magnitude. Again, make sure you know what the question is asking for. Determine what is given and what can be determined from the data in the question. Make a plan, implement your plan, and reflect on the answer to make sure it makes sense. Practice these step by step and become confident.